Hello and welcome to this session of the course Elements of Mechanical Vibrations. In today's session, we are going to focus on the transmissibility in multi-degree of freedom system, particularly when the degrees of freedom are more than 2. We already have understood what a transmissibility is, either displacement or force transmissibility in a single degree of freedom system, and we shall explore as to how the same can be extended and how does it change as we increase the degrees of freedom to a larger value. Now, in the previous few sessions we discussed the natural frequencies, mode shapes of a 2 degree of freedom system. We also discussed the forced vibration response of a 2 degree of freedom system, and we also explored the coupling of different degrees of freedom in a typical vibratory system. Now, in today's session we are going to extend that into understanding the transmissibility in similar such systems. Okay, now let us look at revisit our transmissibility discussion, and in this case the transmissibility will be for a higher number of degrees of freedom. What we discussed in the past was the transmissibility, both displacement and force, for a single degree of freedom system. How does it appear for a multi-degree of freedom system, and some of the important practical insights we will try to derive out of this exercise. So, I am taking an example of again an air conditioner condenser unit which is mounted on the plinth or any civil structure, and it is supported on a mount like this. Okay, so you don't get to see springs all the time, right? Although you always write the governing equation with K representing the spring stiffness, but that spring is physically not always a helical coil spring. It can be a polymeric mount like what you see here. This of course will have its own vertical stiffness, okay, which can be quantified, characterized by testing. Okay, now if you model this as a multi-degree of freedom system, maybe I will represent this unit and mounted on the isolators. Now isolators will be 4 at 4 corners. So you can see that these are the spring location, the mount locations at the 4 corners of this unit, represented by a spring here. Now this spring, even helical spring, will not only offer the stiffness in the vertical direction, but if you try to move laterally, the top the lower part if you fix, and the upper part of the helical coil spring, if you try to push it horizontally, it will offer some resistance. So there is a way of finding out what is the lateral stiffness of a helical coil spring. Of course, it is based on some empirical relation, but it's not so difficult to find them by experimental means. So we will not bother as to how that value of the lateral stiffness or vertical stiffness is actually quantified, but assuming that a mount like what is shown here would offer stiffness both in the vertical direction as well as in the horizontal direction, we will now take into account the stiffness in both vertical and horizontal direction, and the degrees of freedom here would be 3. You can keep increasing the degrees of freedom up to 6 in a body like this, but let's focus only on the vertical degree of freedom, which is y, the horizontal degree of freedom, that is x, and the rotation, that is theta here, which actually means that this whole body can vibrate like this. Okay, can have a translatory vibration like this, and can also tilt, it can pitch like this. Okay, now it all depends on what do you expect. This fan is rotating, so it's a rotating system, right? And the fan may have some unbalance, residual unbalance, so it is going to be like a mass unbalanced mass u and as the mass is spinning with some speed, it will have it will generate a harmonic excitation force. Now there is no way we can assume that the entire mass center is located at the CG of this entire unit. It may not be possible. Okay, so let's take a general case where the position at which the spinning is happening is offset from the CG location by a distance equal to E. Okay, so slight offset in the rotating unbalance position from, I mean, vertically shifted by an offset equal to E. And the distances of the springs are shown here. So the mean, or an the central position of the spring is given by AY, the position of it from the CG location. Similarly, from the CG location horizontally, the springs are located at the distance AX. Okay, and the positions of the springs in the horizontal position, where the axis Z is shown there, that position is AZ. Okay, now you can, as I said, you can also look into considering that there is a yaw degree of freedom. There can be lateral motion which is quantified through coordinate Z. You can also have a roll motion, so maybe alpha here, which is the rolling motion of this box or a unit. But for the sake of some initial uh, discussion on the transmissibility, what we are assuming that the motion is in a single plane. Okay, and then the degrees of freedom are x, y, and tilt, that is pitch motion, which is theta. With this, let's look at um, how we get the governing equations of motion for this unit. Now you all know how you generate the governing equations. Use the free body diagram now for this body, and supposing that this body rotates, and we have discussed this because this is too exaggerated, but let me no, no, let's do this way. Okay, so this box moves all degrees of freedom here, so we have a slightly rightward horizontal motion of the CG. So this CG gets shifted, and it does have of course shown very exaggerated here, but then you will have to presume that this value is going to be too small for our linear assumption to be valid. But just for the sake of clarity, the motion is being shown here, that it is moved up, moved slightly horizontal. Okay, all the motions are independently possible, and then of course some amount of tilt is happening here. Okay, now if this kind of a free body is shown displaced from its initial position, so what are the forces which are going to get generated in this body? That is what we are supposed to think. Now in the case of coupled pitching and bouncing motion, you have already discussed and derived those governing equation of motion. At the point where the spring is connecting the body to the surroundings, those points will be the location of the forces which will get generated. And what will be, so if you are trying to stretch it up and then tilt it and then move it, what is the vertical force which is generated here, which will try to pull it down to its original equilibrium position? What is the force which is going to get created there, and so on. So if I uh, would like to try and show it to you as a three-dimensional view of it. There would be one spring here, another spring here. So there will be this downward restoring force. At this spring there will be another spring on the back side which will pull it down. There will be another spring here which will pull it down. So there are four forces which are going to pull it down. Now how much is the force which is generated at this location? Yes, would it um, be related to the vertical stiffness Ky? Of course, as the spring gets pulled up, this force is going to be Ky and proportional to the stretch. Well, how much will be the stretch? Vertical motion y, okay, but the tilt will reduce it, okay. So this is going to be y minus what? Ax into theta, because if this is tilted by an angle of theta, the stretch here will get reduced by this distance. So minus Ax into theta. Will this be the same force? Yeah, because this body is tilting like this and we are considering only one planar motion, okay. So when it tilts, when it pitches, both the springs are displaced with the same displacement. The net stretch in the left two springs is going to be the same. This unit is going to simply tilt like that. So there is no doubt about this force being identical to the front one. You think about it if you have any confusion on this. What about this force? It will be related to the vertical stiffness, and then make a note that y gets added to this additional tilt motion or additional translatory displacement because of the tilt at the tilt theta. So it is going to be adding here uh, ax theta. We are simply assuming that this distance and this distance, okay, the distance of this spring and this spring from the center here is same. If it differs, the force will be different. You have to take that into account. So G is located horizontally in the center of the distance between two springs. So what about this? Yes, the spring on the back side, that is this spring, is of course going to be the same identical Ky into y plus Ax into theta. This is what the force will look like. Is that clear? Hmm? Will there be only these four forces on this free body? Hmm? Yep. Will there be only these forces? Of course not. Hmm? What? So there will be forces because of the lateral stiffness of the spring. The spring is not only trying to restore it vertically, but if there is a horizontal motion, okay, it is that motion will also getting restored, okay. So just imagine that if the body is not vertically moving but it is just tilting, okay. So just assume that this body is simply tilted like this. So corresponding to this point will get shifted. How much will be that shift? For a very small amplitude angular motion, very small angular motion, if this distance is ay, then will it not be ay into theta? Because theta is, that theta can be with respect to this is theta, okay. So the horizontal translational motion because of theta only is going to be ay into theta. Mind you, this is what is ay, and we are talking of the center of the spring, okay. So you can imagine that this distance is very large as compared to this distance, so we can assume the center of the spring, okay. So this force because of the horizontal stiffness, lateral stiffness of the mount is going to be obviously kx into the net stretch in that spring. Okay. Now this unit is not only moving x, positive x direction, but it's also tilting. Okay. So how much will be the net stretch in it? Not only the horizontal positive x value, but in addition to that, the ay into theta will add up to that, because that ay, because theta is counterclockwise positive assumed here. Okay. So at the points of connection of the two springs, the displacement is going to be ay into theta, and that will be in addition to the lateral motion x. So x plus ay into theta is going to be the net stretch, horizontal stretch in that spring, and the spring is going to offer this restoring force at the point of contact. I hope you agree that this is the same force here. Nothing changes for this point, this position. So this is going to be x plus ay into theta. You agree with that? What about this? Same, with respect to the CG, the tilt is going to create this motion and this motion at both the points, whether it is on this side or on that side. Okay. So just uh, take a note that it's going to be ay into theta, and no wonder that the same force will apply at that corner as well. Same thing. Yes.
The direction will be opposite, because if the body is tilting and one point is coming inside for the other one to the side, same will happen for the if on the right hand side as well.
Okay. So this is, you agree that this is the original point of contact of the spring. Okay. Is it not? And now when you tilt it, this point is shifted here, this point is shifted here. If you are looking at the stretch in the x direction, in both these cases the stretch is going to be positive with respect to the original position. We are not talking about vertical motion here, we are only talking about the horizontal motion. Now that ay into theta and this ay into theta, they will add to the net translatory motion x. Okay. And this is how it is going to look like. Is there any other force that we missed out? We of course have neglected the damping in the mount. Damping will be there, but if you start adding the damping terms here, things are going to be crazy. So let's keep it undamped case at the moment. You can as well look at what happens when the damping comes into the picture. Okay, suppose, yeah, obviously there are four mounts and the body is having x, y and theta degrees of freedom. This is how the free body diagram would look like. Of course, I've drawn the free body diagram as a 3D one, but you can always show all the forces and then get basically your application of the Newton's second law here. So if I apply the Newton's second law, let's say look at vertical motion in the vertical direction. What is that? This is g, of course, in the center. Mass of the unit is, let's say, m. So m y double dot vertical motion. This is, sorry, this is y. Okay, so this vertical degree of freedom y, my double dot will be how much? All the forces in the direction of the acceleration, and the forces are all ky related forces. Kx related forces are orthogonal to it, they will not appear in the equation. So my double dot will be minus ky. Now these forces being identical, I can add them up. Okay, so now it is going to be minus 2 ky into y minus ax theta, and then minus, these will add up to minus 2 ky y plus ax theta. That's it, right? Mass times acceleration is equal to summation of all the forces in the direction of acceleration. If you simplify this, you can definitely see that ax theta term will cancel out, and then I can write this equation as my double dot plus 4 ky into y equal to 0. That's our first equation. Let's look at the horizontal motion. Summation of forces, or apply the Newton's second law for the horizontal motion x, and then in that case mass times acceleration is equal to all the forces in the horizontal direction in the positive direction of the acceleration, and you can see that all of them are opposite, so therefore it will be minus, these two forces are same, and in fact all those forces are same, so I can write this as 4 kx into x plus ay into theta, isn't it? Right? So mx double dot plus 4 kx into x plus 4 kx ay into theta equal to 0. Right? Now, if we assume the radius of gyration about this axis of the body is rg, okay, so about the z axis, if the radius of gyration is, maybe instead of rg we might write that as rz, because it is about z axis. So then what, if you now look at the moments and apply the Newton's second law, m rz square, that is I theta double dot equals, now look at the moments, okay, moments will be, so your theta and theta double dot are positive counterclockwise, so 2 ky into y minus ax theta, right? So this force and this force, both of them are counterclockwise, so they are in the direction of the angular acceleration. Ax theta times this distance for getting the moment, a into ax, okay. The other two forces are going to create moments, so the forces at these two mounts position, they are clockwise, okay. So minus 2 ky y plus ax theta into ax are the moments created by the two forces on the right side mount positions, okay. Now these are only vertical forces, we will have to now include the horizontal forces as well, okay. So if I add to it the forces, and they are all counterclockwise, okay, at the points of contact of all the four mounts, you can see that this force, all of these forces, they are all clockwise, and so they will generate same moment, and I'll club all of them together. So it's going to be 4kx. This kx, this and this all included will be 4 times, because the value of that force is the same at all the mount positions. So it's going to be x plus ay into theta, and yeah, I think that is it, but multiplied by, of course, the moment arm, that is going to be ay. Okay, so multiplied by ay, that's going to be the, oh, sorry, so this has to be negative, isn't it? Because theta is positive counterclockwise, these are all clockwise ones, so they are going to be minus. All right, so this is going to be generating another equation. Now what we have not accounted for is the external force. So if I include the external forces, then the general the governing equation of motion, considering the forces also, is going to be in the vertical direction. This force acts, so F sine omega t. Okay, so and then here this is going to be F cos omega t, and to this I will add the moment because of this force is going to be minus F e cos omega t, because this force is acting at an offset distance of e from the g. Okay, that's it. So this is how these forces are turning out to be, these equations are turning out to be. So this is equation number 2, this is equation number 1, and now I would write this equation completely. So if I pull these terms on the left hand side, I will get basically ax square. So this is going to be plus 4 ay and ax square, sorry, ax square, and then so this term and this term are going to cancel out, and then plus kx, so I can club this one as kx into ay square into theta, and then yeah, plus 4 kx into ay into x equal to minus fe cos omega t, and that is going to be my equation number 3. Let's see, these are the two equations. Of course the third one is not written. uh, what do you see from the three equations? How do you qualify the first equation as, if you really look at the first equation carefully, that equation number 1, which is, will you call that as a bounce motion? Yes, it is moving along y, and that bounce motion is pure bounce motion. Do you see that that motion, or that governing equation, defines the dynamic response along y direction without any term of theta or x? So that means it is completely decoupled from x and theta. Okay, which means that the condenser unit can simply move vertically up and down without generating an simultaneous tilt or horizontal motion. Okay, that's what it is showing. And then what is the natural frequency? Py. If I define for the vertical motion, I can set this external force to 0, and then it will be my double dot plus 4 ky y equal to 0, which gives you the natural frequency square root of 4 ky by m. That's the natural frequency of the system. What about equation 2 and 3? Okay, this is your sway motion and this is your pitch motion. Yeah, pitching and swaying is coupled. Okay, you can physically look at this box, this condenser unit, or in fact you imagine your car body, and imagine that it's a toy car so that you can actually fiddle with it. So if you try to move this car body or this condenser unit horizontally, you imagine that it is going to tilt also simultaneously, right? And why does that happen? Because your mound locations, the restoring forces generate an unbalanced couple to create that kind of a theta motion. Okay, any horizontal motion is going to immediately simultaneously generate forces to create that kind of a tilt motion. Okay, so the horizontal x motion is coupled with the theta pitch motion, and the mathematical manifestation of that physical coupling motion is shown here, that the equation of motion in x and equation of motion in theta shows up, or also have the terms related to theta in the equation of x and terms related to x in the equation of theta. Okay, and the quantities that create this coupling, what are those quantities? Kx and ay, right? You imagine that if the spring does not provide any resistance to the horizontal direction, would it generate any pitch? No. X motion will or y motion of course is completely decoupled, but the theta motion will not generate any x because there will be no resistance in the x direction. But practically, because every mount or anything that you use for supporting such a body, that is going to generate resistance. The spring, even the helical coil spring, which is designed to take the vertical load, that will also provide horizontal stiffness. So now the only realistic physical parameter which is creating this coupling is actually ay. Okay, so this ay is the parameter, so it appears here, and that ay is coupling the motion in x and motion in y. Okay, so these are the governing equations of motion that we have obtained, but you would wonder what has transmissibility to do with all this. So we are actually now going to move towards looking at the transmissibility um, of the forces, and that is something which is the next point of discussion. So once with these equations obtained, now we get back to business, in the sense that we define some non-dimensional parameters, like frequency ratio is defined as the ratio of the excitation frequency. F, mind you, f cos omega t and f sin omega t are the external forces. So they are fluctuating with forcing frequency omega, which we normalize with py, because py is decoupled natural frequency, and we would like to normalize it with that. Not that we cannot do it with other, but that is more sensible way to do. Vertical static deflection is defined for, again, based on f by net vertical stiffness. Net vertical stiffness provided by 4 springs is 4 ky, and the stiffness ratio eta is defined as the horizontal to vertical stiffness of the spring or the mount. With this, if you substitute the assumed solution, again I would emphasize that we assume harmonic solution, because and harmonic with respect to the excitation frequency. So x equal to capital X e power j omega t, damping is not there, and theta can also be capital theta e power j omega t, and yes, y can be also appropriately chosen. And then you are now quite conversant about how to get the response expression or the amplitude. So if you do that, substitute everything, use these some of the non-dimensional parameters that we have defined, you will get this expression. So again, it's a straightforward mathematical exercise to figure out that the amplitude in the horizontal direction is given by this expression, normalized with respect to the static deflection. Looks very um, very complicated, long expression, but that's how you get it. We would, try to get some inferencing done from the graph that shows the variation of this x with respect to some of the parameters. Now the common parameter would obviously be um, the frequency ratio, right? um, let's see what we plot. The other expression for theta would be this. For y, we don't have to worry about y, because you know what kind of an expression are we expecting for y over yst. Yes, if you can't tell me this, then it's a serious problem, isn't it? Simple, because there is no damping, zeta does not come in the picture. Okay, so this is what y will be, and then this is what theta will be, and yeah, that's it. So can you tell me how do I get the resonance frequencies? The resonance frequency in the vertical direction, we know that so omega resonance would be what? Square root of 4 ky by m. So very simply, that is the natural frequency. The resonance frequency in the vertical direction, the omega y, will be this. What is the uh, resonance frequency or natural frequency in the x and theta? Now mind you, we have already seen that the equations are showing coupling between x and theta. So the frequency that you get is going to be coupled pitching and swaying natural frequency. Okay, so we will get what? Px theta, px theta 1, px theta 2. How do I get that? We have done this in 2 degree of freedom system. Once you get this response expression, this response in absence of damping, this response will go to infinity at resonance theoretically. And when will it go to resonance, and when will it reach its maximum or infinite value theoretically? When the denominator goes to 0. So if you equate this denominator equal to 0, that will spring up to resonance frequencies, and which are going to be the natural frequencies. Now you make a note that the denominator in both cases is exactly identical, and that denominator is quadratic in r square. That is going to give you the two natural frequencies, px theta 1 and px theta 2. So if you solve this denominator equal to 0, which is going to be this expression, you're going to get the expression for the two coupled natural frequencies. So again, this expression would look little offending. It's not a very sober simple equation, but then that's how it is. We are uh, dividing and multiplying it with some terms just to keep it non-dimensional, or basically to get this right hand side expression um, appropriately formed, so that we can plot it properly and then derive inferences from it. So px theta is now normalized or divided by py, and the numerator and denominator is also multiplied by rz and ax. That's how this particular equation was formed. Okay, so don't worry, this expression is going to give you two values of px theta, the coupled sway and pitch motion. The first one will be with this negative sign into account, and the second one px theta 2 will be with the positive sign accounted. Okay, so two of these two signs will give you two different coupled pitching and bouncing, sorry, not pitching and bouncing, pitching and swaying px theta 1 and px theta 2, two natural frequencies. So this is all algebra or simple mathematics, which I'm skipping here, so as to focus more on what we learn from these equations and the variation of it. So what is going to happen is that we are going to plot those frequencies. Before we do that, it would be nice to comment on what parameter is important for decoupling. And we know that when ay, which is this parameter, is 0, x is independent of theta, and when that is equal to 0, this term goes to 0, and then you will have equation only in theta. That means you have a pure pitch motion, and that will happen if I somehow support this condenser unit over here instead of supporting at the base. Okay, and maybe I can show this spring to be here, so that the center of the spring is not even having this much offset. Okay, so you can in fact show that the spring is located here and the spring is located here, so that what will be the position of the spring? It is almost along the g axis, which means that this ay is 0. So physically, mathematically, it is ay equal to 0, but physically is like hanging it at appropriate support points, so that the coupling is not there. Yeah. Yeah, so you don't see that because people don't mind having larger force being transmitted and so on. Now, of course, the next slide is more important, that will give you some idea, but it is actually implemented in big machines if you have, and instead of supporting it here at the corners, what they actually do is, if they cannot hang such a heavy machinery here, which is actually what is indicated in that particular illustration, what then is an alternative is that you support it here, no problem, right? You support it here, but you attach a heavy concrete mass, so that you shift the g from here to here. That is the same thing, right? Either you make ay equal to 0, or let ay be effectively 0 by shifting the mass, the cg of this whole unit. So these machines are then extended, and they are the lower part is put in a pit like this, so that the decoupling happens. Now, but the major question is, we are all the time drumming about getting the decoupling done. On what basis do we say that this decoupling is going to be useful? So the question now is looking at how this decoupling helps in terms of transmissibility. Okay, now these decoupled frequencies would obviously be these. Of course, if the decoupling is there, this was anyway originally decoupled, but then when you decouple it by setting ay equal to 0, you basically get the frequency px to be what? Square root of 4kx upon m, isn't it? And what is kx? We have defined a stiffness ratio eta to be what? Kx upon ky, didn't we? This was defined as the stiffness ratio. So then if I substitute for that, then I get 4 eta ky upon m, which actually means square root of eta into, sorry, this is equal to square root of eta into py. That is what this is. And of course you can also show that by appropriately manipulating those terms, that the p theta can be shown to be this. Okay, so these are the decoupled natural frequencies of the system. All right, let's then plot this px theta, which for which the expression has been already obtained by us in this expression. Px theta is giving you the two coupled natural frequencies, and on the and what do you plot it with respect to? We plot it with respect to this parameter, square root of eta rz upon ax, which is basically this parameter. Now we will have to plot it against some parameter which are, you know, something which is going to change with the change in stiffness, or with the radius of gyration, or the position of ax. So now we plot these frequencies with respect to this parameter. Okay, and if you look at this expression, p theta, pure p theta is a function of ax by rz. So it makes sense to plot it this way. The plot of coupled pitch and bounce, coupled pitch and sway motion, natural frequency to that is plotted with respect to a parameter which is shown here. What do you get? First, we also plot the two decoupled natural frequencies. So px, which is the expression that we have obtained in the previous slide, that px is square root of eta into py. That is the expression that we have. Okay, so it is plotted as this line, and p theta is plotted as this line. Now the p theta, for ay by rz equal to 0, the p theta line is going to be located at point at the value 1, which is going to be the line corresponding to pure pitch natural frequency, and this line corresponds to pure sway natural frequency. So these two lines are drawn here, and for other values of ay by rz, non-zero values, they are plotted. Then when ay by rz becomes not are not 0, because we know that it's only when ay is equal to 0 we get decoupled natural frequency, obviously. So these two lines representing decoupled natural frequencies would mean that ay is equal to 0. But ay, if it is not 0, then ay by rz equal to 1 and ay by rz equal to 2. These two natural frequencies are like px theta 2, px theta 2 for ay by rz equal to 1, and px theta 1, and this is for px theta 1, for two different values of ay by rz. Huh? Are you confused? What we have done here is that we are plotting the coupled natural frequencies px theta 1 and 2. When ay is equal to 0, they automatically translate as pure pitch and pure sway natural frequency. So they are like px and p theta. When it is non-zero, ay is non-zero, let's say ay by rz is equal to 1, then the higher of these two natural frequencies, px theta 2 will be following this variation, and px theta 1 will be following this variation. Let's stick to only these three of them. Forget about this value. These are for different values of ay. Okay, larger ay means what? 0 ay means you're completely decoupled. You keep on increasing the ay, you increase the amount of coupling. Clear? Now you consider that the parameters of your system is corresponding to this position, wherein, okay, wherein your AY is 0, suppose. What are the two natural frequencies? One will be here, another will be here, right? Think about that. You are able to decouple it. AY is set equal to 0, your system is like that. So for this particular parameter values, the two natural frequencies are going to be this and this. Now recall what you learned for a single degree of freedom system. What did you learn? Recall that this is our magic point. Don't forget single degree of freedom. It's going to, this is transmissibility ratio. What do you design for? Very low transmissibility. This condenser unit is expected to transmit as low forces as possible to the foundation, so that the building doesn't vibrate, doesn't create sound. So would you like to be on higher side of R here, isn't it? Now higher value of R, I told you that typical design would like to have R greater than 3. 3 is a tentatively ballpark figure, not a mathematically defined or a derived quantity, but typically greater than 3 is good. What is R? Omega pi p greater than 3, which actually means that the p should be, now your omega is already decided. For that omega, your p should be less than 1/3 of that excitation frequency, right? So ideally, what is your design consideration? You would like to have your natural frequency as low as possible, right? When we were discussing transmissibility in a single degree of freedom system, what we also looked at, that if omega are multiple in numbers, 1 omega, 2 omega, 3 omega, higher harmonics of omega, if you design it for lower omega, it is fit for all other higher omegas. Okay, now here the condition is different. You have multiple p's, you have many natural frequencies to account for a single omega. In this particular case, assuming that there are no higher harmonics of the excitation frequency. Now so if this is the case, which omega will you consider for the best design? So supposing that you have two, you have px theta 1 equal to, let's say, 10 hertz, and then px theta 2 equal to, let's say, 28 hertz. If this condition is to be satisfied, which p will you be concerned about for the design? 28 hertz or 10 hertz? So when you are designing, see, you designing means what? You will fiddle with the value of the stiffness, right, of the mount, so that your natural frequency is less than 1/3 of the excitation frequency. The condenser unit is, suppose, operating at, let's say, 16 or let's say 46 hertz. I mean, hypothetical case, it's not going to rotate at that higher speed, but just assume that it is 46 hertz, right? Now, what is your P expected? 46 by 3. Oh, I chose a wrong number. What will be that? Roughly 16, slightly less than 16, right? So this is going to be a problematic case for you, right? You expect your natural frequency p x theta 2 and p x theta 1, either of them should be less than omega by 3, which is to be less than 40, let's say instead of 46 I will take it at 48 hertz. 48 hertz divided by 3, that's going to be 16. But you have a problem here because px theta 2 is 28 hertz, which is higher. So although it is still going to be fine because it might be uh, uh, slightly close to square root of 2, right? 1.4 and 28 and then 48, it's still going to be a problem. Yeah, it should be greater than 2, but then generally we expect the ratio to be, let's say, 3. So we would like to take care of this take care of this px theta 2, try and reduce it as close to 16 as possible. Okay, are you worrying about px theta 1? You are not, because in this case the higher one, if you account for, the lower one is fine. The lower one is always going to be fine, right? Okay, now so this is 28 and this is 10 and you are fine. Okay, but if your system is, let's say, coupled, not decoupled, if your system is now assumed to be coupled and not decoupled, then where are you? Let's say, depending upon the value of this ay by rz, ay non-zero means it is decoupled, sorry, it is coupled. So where are you? You are here and you are here. One of the two natural frequencies, px theta 2 is here, px theta 1 is here. Okay, if you were decoupled, these were the two natural frequencies, but the moment you have coupling, one of the two is going up and the other one is going down. The one which goes down, you have no problem with it. This 10 hertz, okay, this 10 hertz dropping to, let's say, 5 hertz or so is no issues. This 28 hertz going to 38 hertz is a big problem. Clear? So the moment you have a coupling, the larger of the two coupled natural frequencies are going to be problematic from the transmissibility viewpoint, because instead of you being here, you could be working here. Right? That's the problem for you. Okay, and no matter what you do here, if you take some other operating condition, some other set of some other parameters, you are always going to have the decoupled natural frequencies to be smaller as compared to at least one of them, one of the coupled natural frequencies always going to be higher than the higher of the decoupled natural frequencies. So the higher of the decoupled natural frequencies is this, your one of the coupled natural frequencies always going to be higher than that, right? So this is what the designers always try to decouple the system, and the best way and the most practical way of doing it is holding them at an appropriate positions. Okay, you open your car bonnet, you will find that the engine is not supported at its base, it is supported at some other point. Okay, in general they tried to reduce the amount of coupling. Larger the value of ay, stronger is going to be your coupling. Okay, this graph essentially helps us understand the philosophy behind decoupling of the motion, and it has a direct bearing on the transmitted force. The moment you have a larger frequency, one of the natural frequencies, the amount of transmitted force is going to be larger. Okay, because that graph which we learned for a single degree of freedom system is always going to increase the level of transmitted force if the frequency is increasing, natural frequency is increasing, because r is going to reduce by that. That's the philosophy. So therefore you should not be bothered about the complicated expression that you have, what you have been able to understand, that if you plot this expression that we have got, the learning from the graph is more important than where and which particular term is up. Of course, they are all perfect and correct terms there, but they do teach a lot through this graph when we plot that graph about its implication on the transmissibility. So irrespective of where you go, you will notice that the coupled natural frequency is always going to be higher. Okay. So as I was discussing, this huge machinery, you won't find them. I mean, good design would not support it here, but then what they do is they would probably, if this at all support it here, they would put some mass and would ensure that this G originally which was here would be shifted down, so that the amount of AY is going to be reduced. Okay. And I mean, the other alternative, if you can manage, is to support it here and have less amount of additional concrete or any other mass to be fitted there to shift the CG down. Okay, so that's the practical way of getting around decoupling of the system. So ideally, a compressor, which we have seen, this should have been supported here, but of course we all don't care so much about the noise and vibration in the day-to-day life. This design is not going to generate quieter systems. The force is going to be going on through this mount to the foundation is going to be much larger, and then that force is going to create vibrations in the walls, and that is going to create sound inside the room, and that is the way it should be. Okay, summary of this lecture, we explored and understood the transmissibility as it applies to more than 1 degrees of freedom, and in particular we saw that the decoupling of modes and its correlation to the transmissibility, and this will help the designers to ensure that the transmitted force is minimized to the foundation. Based on what we discussed in today's lecture, a simple question for you to answer. That is the answer for this question.